if you're not familiar with Quantinuum, we've existed in a couple different forms for the last sort of six-ish years or so. I started on the Honeywell side, so Honeywell Quantum Solutions, and about a year and a half ago we spun out of Honeywell, so we're separate now, and then merged with Cambridge Quantum Computing, which is a software company based out of the UK. So now Quantinuum, we've got offices in Broomfield, Colorado, Minneapolis, Minnesota, London, Cambridge, Oxford, Munich, and Tokyo. So the hardware is all sort of split between Colorado and a little bit in Minneapolis as well. So our quantum computers are these trapped ion quantum computers. So they're big room-sized things that look like something you'd expect out of a university lab. The H2 system I'll be talking a lot today about sits on two 5x20 optics tables, so really a room-sized thing. You could probably fit 2 of them in this auditorium here, maybe 3 if you really scrunch them in. So big things, lots of electronics up top, lots of lasers and optics, but all of that just provides classical signals that go down to the ions. So the ions sit on a surface electrode ion trap, and they're confined to a space about the size of a grain of rice, a couple millimeters. And everything else is just classical control manipulating those ions, which are our qubits. So here's our glamour shot of H2. It's this racetrack trap where they're confined to this oval here in the center. Our qubits are ytterbium-171 right now. We use two hyperfine states in the electron ground state as our qubits. These are clock states, so they're fairly insensitive to magnetic field, which means without a whole lot of effort, we get 5-6 seconds of coherence time. We also have barium atoms in there for sympathetic cooling. We move our ions around and they get hot, meaning they have motional excitations. That doesn't affect the qubit state, but we have to cool them back down before we do entangling gates. And so we cool down the barium atoms, which are in the same well as the ytterbium atoms, and then we can perform our quantum computations without messing up anything that's going on with the qubits. Oh, there was, so here's, zoom in on the trap there. There's the top metal layer. You can see we've got different regions where the electrodes are configured differently to do the different things that need to happen. And here's a fun image we made a while back, transporting 32 qubits around this racetrack. And that's where it sits today with 32 qubits. Of course, we can fit a whole lot more in, and we're sort of working on the upgrades to improve the machine there. If we zoom in on the gate zones, this is where all the action happens. Right now, we're just using the bottom 4 gate zones, or I guess the right 4 gate zones in that vertical image I showed you there. The ions sit in these four ion chains, 2 qubits, and then 2 of these sympathetic cooling ions. And laser beams are sort of fixed in these locations to perform all of our quantum operations. So we do single qubit gates, which are just Raman transitions between those 2 hyperfine states, and then these 2 qubit gates that use a pair of laser beams to impart a spin-dependent force and do a Mulmer-Sorensen gate with the two qubits there. You'll notice the electrode structure is a little complicated in these gate zones. We have these thinner electrodes. That's so we can better sort of split the ion chain apart, and then even do rotations where we can swap the order of any of the qubits in that chain. So we call this the QCCD architecture. That was a phrase coined by some researchers at NISQ quite a while back, where they said, well, just like the electrons on the backplane of your CCD camera sort of shuffled around to read out an image, similarly, we're going to move our ions physically around between different zones for measurements and gates and things like that to do a quantum computation. So the qubits are mobile and the zones are fixed. So a little different than a lot of other architectures you might be used to. And because of that, I'll walk you through an example and sort of how this works. So on the left is a quantum circuit I invented solely for the purpose of being easy to animate, but it has all the elements you'd see in a real quantum circuit, so this is nonsense, it does nothing. And on the right, you've got a schematic of the trap, so those darker gray regions are have the qubit, the H2 system. We're doing a little bit better than that on H1 now. We've done a couple more upgrades there. We think we should be about the 3 nines level for both these systems within the next 6 months or so. And then, a criticism of ions is always that they're very slow. I won't argue with that. They are slow compared to many other technologies, but our coherence times are long enough that this sort of memory error you get, so the decoherence you get during the time it takes you to shuffle all your qubits around and then do the gates in these sets of batches, is fairly low. So the memory error per depth 1 circuit time, so at the time it takes to completely arbitrarily change your circuit, or the pairing of your qubits, and then do a gate on all possible pairs, that's 16 different 2-qubit gates in the 32-qubit machine here. The error we get from sort of decoherence over that time is 6 × 10⁻⁴. So larger than our single qubit gate error, so it's something we're working on, but far lower than our limiting error, which is our 2-qubit gate error. And then qubit measurement reuse is something we're very excited about in the NISQ era. And I'd say, it's fairly easy to do in the QCC architecture, but everyone's got to get better at this because that's how error correction works, right? You've got to measure things out and do things in real time. So some things you can do with this qubit reuse. The first thing you'll realize is there's a lot of circuits where you don't use all the qubits all the time. So this is a max cut QAOA experiment. I'm showing a sort of truncated example with only 7 qubits here. Is that number right? No, it's more than that. With some qubits here on the left, and if you were to stare hard enough, you'd realize that some of these qubits are done before other qubits even begin. So without changing anything about the circuit, you can compress the circuit down from 10 qubits or whatever it is down to just 4 by using these measurements and resets in the middle. And so with that, we published something on the archive a little bit ago. It's going through peer review right now, where we did an 80-qubit sort of max cut QAOA circuit just using the 20 qubits on the H1 device. So for many circuits, especially if they're very wide and very shallow, you can run larger circuits than you might expect because you can just reuse your qubits over and over again. And in fact, in this suite, we show that there's a classical algorithm where you can put your circuit in there and use a sort of a greedy algorithm to figure out how you can compress the circuit maximally to a smaller number of qubits. Another fun thing you can do with qubit measurement and reuse is you can create these long-range entangled states. Here's a circuit you get to do a GHZ state, so you want your qubits to all be in a superposition of 0 and 1. You can do this just by using these C0 ladders that we're used to here, or you can do local C0s, measurement and the classical feed forward to create that same state. Now the GHZ is a little bit contrived because we have long-range interactions, so there's actually less gates to do it the way on the left than the way on the right, so we get better fidelity, fewer gates. But we recently had 2 different papers where we talked about some way you can get interesting topological states using just these local entangling gates, and you can beat this Lieb-Robinson bound, right? So instead of having to have a series of gates that get information all the way across your chain, you can do local gates and then feed forward to get these long-range entangled states with constant depth for your circuit, which is kind of neat. All right. And then, of course, quantum error correction. We've done some interesting demonstrations on quantum error correction. Not enough time to go into it, but I'll encourage you to read the papers. The first one is the first demonstration of sort of repeated rounds of fault-tolerant quantum error correction. So measuring both these flagged and unflagged syndromes on a color code here, and then doing repeated rounds of quantum error correction with real-time feedback. And then more recently, but also up on the archive, we showed better performance with a logical 2-qubit gate than our physical 2-qubit gate. So these numbers look a little bit low because spam is included here, but sort of a nice step. We're not quite to the break-even point yet, but we'll have some more demonstrations on that coming in the near future. So back to this slide, I said we're very excited about our performance with our fidelities here, and we take benchmarking very seriously. You'll see there's a paper up on the archive where we walk through all of the benchmarking we did on this H2 system. We use randomized benchmarking for just about everything we can. So you'll see single qubit randomized benchmarking, 2-qubit randomized benchmarking, always done in parallel using all of our gate zones simultaneously. And then also memory randomized benchmarking where you do SQRB. Oh. Okay, put it in here. Mike, just hold. No, it's all right. No point speaking if you can't be heard. Okay, is that better? Wonderful. Yes. All right. So we do all this randomized benchmarking. You'll see we post all this data up on GitHub, so you can see not only the circuits we run, the data analysis we do, and all the raw data. Here are the numbers from the H2 machine. Not quite a hero run, but
I would say, slightly better than typical. So a little better than what we have on our data sheet. Here we've got 1.8 10 to the minus 3 for our TQIB error, which is sort of the limiting error, but very low for crosstalk and spam and NISQ as well. So you can see all of that data online if you'd like. That sort of transparency is very, very important to us. We also go into a little bit more detail describing these experiments in this paper, which is up in the archive. This was sort of the coming out party for H2. It's 30-something pages long, so there's a lot in there describing the trap, and then also all the benchmarking we did there. Just because each of your individual components works well, though, doesn't mean that your circuits are going to run well. We've all seen things that fall apart that way. So we really like to run more holistic benchmarks as well. One we've run a lot is quantum volume. This was invented by IBM back in 2019. If you're not familiar, it's a random circuit. So if you have n qubits, you have a depth n circuit, where each step you randomly permute your qubits, and then you run an SU4 sort of fully arbitrary 2-qubit gate on it. So for us, that's broken down into 3 ZZ gates. We can't do an SU4 in a single step. So it's permute all the qubits, run an SU4 on all pairs, permute them again. You do that n times for n qubits, and then you compare what you get to what the expected is from a classical simulation. So it's not always clear how to compare distributions here, but what was laid out is you sort the list of all the different state vectors you can get according to their probability from the classical simulation, and then you just count how many times did I get one of these heavy outputs, the 50% more likely outcomes. This might seem like a bad way to judge how good a quantum circuit is, but there's some good math behind this that shows that for a random circuit, it's easy to see you just get 50%, so that's bad. You couldn't tell anything about it. And if you had a perfect quantum computer, sort of in the large n limit, you'd get 85%. So there's an arbitrary threshold at 2/3 that if your quantum computer gives you these heavy outputs 2/3 of the time, you've passed the quantum volume test. Good math behind it, most of which I don't understand, if I'm perfectly honest. We recently done 2 to the 16 on both the H1 and the H2 devices. So on the left, you can see all the individual circuits of each specific randomization, what its heavy output probability is, and then this dark blue line is the running average, and then the confidence interval coming down as we take more and more data. So we passed that 2/3. When we first released our first quantum computer, H0, with just 6 qubits, and got a quantum volume of 64, the CEO of Honeywell, who's now the chairman of the Quantinuum board, said that we were going to improve our quantum volume by a factor of 10 every year for the next 5 years. And that's what that dashed line is. So important for my job reviews that I stay above that line, and for the most part we've been able to. I think it's a really good forcing function in that it focuses you on everything, right? It's not just qubit number, it's not just fidelity. Everything matters, memory errors, spam, it all comes into play for quantum volume. So it's been really good to push sort of as hard as we can on everything all at once to stay above this line. So quantum volume is one we like. Of course, it's not the only thing. There's a lot of circuits out there that don't necessarily look like random block circuits. So in this paper, we also did mirror benchmarking, which is closely related to quantum volume. Random circuit sampling, this is cross-entropy benchmarking that Google did. So very good performance. We only got to 32 qubits because that's all H2 has right now, but sort of very high fidelities at 32 qubits. And then we also made this GHD state, which was a lot of fun. Sort of largest fully bipartite entanglement on any quantum system. There's also some other demos in this paper. Hamiltonian simulation, quantum dynamics, we did another QAOA experiment, and then classical error correction. This is a repeater code, so you can see it just sort of pegs it at 1 as we go to larger distances there. So cool demonstrations really showing what can be done on this H2 hardware, but not enough time to go into all of them today. You can access this computer. We sell subscriptions. I will warn you, they are expensive, but please talk to us and we can talk about that. But one really nice thing is Oak Ridge National Labs in the United States, they have this quantum computing user program where they have bought a subscription and then they farm that out to their users. Their primary user focus is people in the United States with Department of Energy funding, but they open it up to anybody. So you can go onto their website, you can fill out an application, say here's what I want to run, and they'll hand you some small bucket of credits. If you do this and you don't get very many credits, don't worry, that's just how they operate. Run something, and then come back and say, this is awesome, I need more. So if you want access to the computer, you can do it through Oak Ridge. Microsoft Azure Quantum also has a credits program where you can go online and submit a little proposal and they can give you access to it as well. So those are probably the easiest for academic budgets to get access to the H2 system right now. And then, just because I like to say as often as we are hiring, so look at that too. But this is a NISQ conference, and so I wanted to start us off by saying some explanatory things so people will find me at coffee breaks and argue with me. So I will say we are not quite in the NISQ era yet. Maybe Google with their demonstration could claim that they're there. They're doing something that maybe can't be simulated classically yet. But with 32 qubits here at Quantinuum, we're not there. We're at a really fun point in that sort of our brute force state vector simulation we do now takes longer on a decently beefy GPU box than it does on the actual hardware, which is exciting for us. We're starting to see that these things are quite hard classically, but with 32 qubits, you can just brute force it, especially if you have access to supercomputers and things like that. But H2 is going to be upgraded in the next year to larger than 50 qubits, and there you're really getting to the point where brute force simulation won't work anymore, even with sort of some of the largest computers on Earth. And so we're starting to get in a regime where sort of quantum advantage is possible, and that's where I'd really say that NISQ algorithms start to get interesting. Okay, so we're not there yet. We will be soon, so this is the right time to sort of start doing all these algorithms and verifying that things are working like we want. But I will say that fidelity is everything in this NISQ era. The QCC architecture and ion traps sort of have an advantage here in that, you know, with 32 qubits, I've got 32 qubits around that ring of the circle. You can draw all the lines everywhere. And it's fun to do because it's pretty, right? But that's 496 different pairs, but I don't need to calibrate 496 different things. I need to calibrate 4 gate zones. And so because we pair them up and then drag them through the same gate zones over and over again, we see the same fidelity on all pairs of qubits without too much work there. So our qubits are all identical by nature. We just don't mess them up and you'll be fine. And we have to calibrate some small number of gate zones to get this connectivity, and that's sort of what gets us at these sort of 99.8 2-qubit gate fidelities we have. So fidelity is everything, and here's why. I'll call this the quantum megahertz myth. If you're old, you'll remember back when AMD and Intel were sort of, you know, competing on megahertz speed when that really wasn't necessarily the thing that always mattered on a classical processor. I think often we get stuck talking about the speed of operations when we really want to talk about speed of solution, right? So you can run lots of shots really, really fast on different pieces of hardware compared to ion traps, but your signal really depends on the fidelity. So sort of, if you're going to measure some expectation value of something, and there's noise on your computer, you can improve your signal by taking more and more repetitions, more and more trials, more shots. But that only lowers your noise by the square root number of trials. We all know this is easy. But the signal to noise is going to be the fidelity raised to the number of 2-qubit gates, roughly, right? Every circuit's a little different, but that's roughly what you're looking at. So as you get to these really deep circuits that classical computers are going to have a hard time competing on, the fidelity is going to win every time. So with large enough gate counts, which is where we want to be, because we want to do something you can't just do on your laptop, fidelity is going to be important. And I would say that the number of 2-qubit gates also depends on your connectivity, right? So if you've got this all-to-all connectivity, you can pair up any two, but if you're stuck in some fixed topology of your trap, it's going to take you many 2-qubit gates to get the information between 2 qubits. Now you'd say maybe your algorithm doesn't need that, but I would argue that if your algorithm only has local connections, then your algorithm is probably efficiently simulated by sort of matrix product state techniques, right? If all you have is local entanglement, this is probably not a great NISQ algorithm to begin with. You want to go to something very hard where you have long-range entanglement, and all connectivity is going to be a win there, I think. So now compared to some mythical superconducting device that I'm sure you will tell me is all wrong, but if I say you only need 3 times more gates on a superconducting device to swap the information around as compared to sort of all-to-all connectivity, and I compare this 99.8% fidelity to 99.5, then on the left is the speed of ions compared to speed of superconductors, and on the x-axis here is the number of 2-qubit gates. So you start out a factor of 1,000 faster. That's just the reality of the speed of 2-qubit gates on ions compared to superconductors. And so in the regime of just 200 gates or so, you can do much better as far as speed to solution on a superconducting device. But this is where it's easy to simulate things classically. This is not where we want to be for the NISQ era. If you get up to, say, 1,000 2-qubit gates, which is now much harder to classically simulate, now it's a factor of 10 million times faster to solution, even though the individual gates are a factor of 1,000 slower, right? So fidelity really matters here. Now, this is not just to say ions are the best, although I might say that. I think it's also to say that fidelity really matters. So if you were to take this 99.5% and just raise it up to 99.7, that's a factor of 100,000, faster, right? So I don't care what technology you're in love with. We all have our reasons. Fidelity is what needs to be focused on, so we can get solutions in a reasonable amount of time. So now that I've offended everybody, I'll tell you sort of what we're doing to do the things I just told you we don't care about, which is to get to more qubits and to get faster, right? So I would say for the NISQ era, having enough that you can't classically simulate it is probably enough, but you want to get to larger for many reasons. So we already have sort of this linear trap and this racetrack, which were good steps for us to get to larger qubits. Next, we go to a two-dimensional grid. The sorting time scales better here. You get a quadratic speed up in your sorting time. So although I talk about how speed doesn't matter too much, it still matters. And then as we go to larger and larger, we've got to integrate optics because you can't skim your laser beams across the surface as you get bigger and bigger. And then eventually we have to start tiling things together, which actually Winnie Hensing's group up at Sussex is demonstrated for us. That's really nice. Well, not for us. They did it, but now I say, it was not tricky, so we should be able to do this too. So we've got these pretty photos of ions in our trap running around in circles. The grid, we're not really commercially still for a little bit here, but we have grid traps working and we have ions going around these junctions. This reminds me of Pac-Man, which is kind of fun, but I don't know what the ghost would be. So we have grid traps that are working here. So we are working to get bigger and better and faster, all those things at once. And with that, I'll toss this back up because this is some important stuff, and once again mention that we do have a few positions online, and over the next couple months, I think more will be. So thank you for your attention.